My name is Junior Wachiku. This is Physics 2211, Lab 2, Projectile Motion. Here's my table of contents. First, we'll start with introduction, and then we'll move on to fundamental principles, to procedures, and then data analysis and conclusions, and then possible errors and further questions. Okay, for introduction, we have the purpose of this lab is to analyze the motion of a falling object as well as the forces on the object. The observed motion will be compared to two computational models, one without drag and the other accounting for drag and gravity. This lab will demonstrate the principles of Newton's second law and the effects of the drag force. Our system is the balled up paper that we use as our ball. Surroundings is everything else, which could be like gravity, air resistance, etc. The observed position is the tracker data, and the predicted position is the closed script. Some fundamental principles. First, you have the gravitational force, which is an attractor force that pulls objects with mass toward each other. Newton's second law, which is a momentum principle, whereas an object's change in momentum is proportional to the net force applied. And the drag force, a resistive force that opposes the motion of an object through a fluid. Here's some equations we'll be using throughout the lab. Velocity and position update formula, which is BF equals BI plus F net over M times delta T. And then XF equals, you could use RF equals RI plus velocity average times delta T. And then gravitational force. And this, just note that acceleration due to gravity on Earth is at 9.8 meters per second squared. The drag force. The drag force opposes the direction and is the resistance an object feels when moving through a fluid. Also note that we'll be using Newton's second law. Force equals mass times acceleration. The acceleration on an object is equal to the net force divided by the mass of the object. Here's our procedure. First, we'll lay down a meter stick as calibration. As a calibration stick, record a video of the balled up paper ball being thrown from one side to another. Import that video into Tracker and track the position of the ball using Tracker's tools. Use GlowScript to create two computational models of the ball's predicted position with the use of the starter code, one without drag and one with both drag and gravity. Using the X position and time graph, import to Google Sheets to create a single graph to compare, and then compare the models to reach a final conclusion. Here's our video. Okay, one more time. Oh, go. Okay. Here's our experimental setup. This is the video in Tracker with all the points plotted. The initial position I just set to 0 as it's starting from rest, and the initial velocity is 0.374. In the X direction, 0.374 in the Y direction, and 0 in the Z direction, meter per second. The mass is quite small, which is 0.0027 kilograms, and the gravity is, like I said, 9.8 meters per second squared. The total time was 1.45 seconds. Here's the observed position graph. Just note that we flipped from negative to positive for better accuracy. Here's our computational model. Here we changed the mass, we changed the position of the ball, the velocity of the ball, delta T, and this is like size of each timestamp, gravity, drag force that we've got, and then we've used the position update and the velocity update here. Okay, and then projected models. Here we have without drag. You can see the force of gravity going down, and with drag you have that little drag arrow going up, the orange arrow, and the force of gravity still going down. And here are the graphs that come with it. Any possible errors? The ball shape was not ideal since it was a paper ball and not perfectly spherical. Any human error when placing the axes or the center of mass and tracker, and like any outside forces like air conditioning, just anything that could be used. But what does it mean in what if? What does it mean? The model with drag shows terminal velocity because the slope is gradually getting smaller. But what if the ball were thrown straight up? If the ball were thrown straight up, the time it would take to reach a starting position would be longer because the ball would go higher than if it were thrown in a parabolic path. All right, thanks. Bye.